by way of a brief introduction, he did all of his education at Caltech, right? And joined NIST shortly thereafter, and also became a faculty adjunct at UMD, and has sort of been with us ever since. So we're really excited that he could be here today. We've had certainly some difficulties and upset with the scheduling of JQI seminar speakers, and Kartik graciously sort of volunteered to step in when we had some last-minute cancellations due to federal events. So anyway, thank you very much, and we're really excited to hear what you have to say.
Great. Thanks, Nathan. Guess I should fix this somewhere. Is this okay? All right. Go back a slide. Great. Yeah. So thanks, Nathan. I want to thank everyone for coming to the seminar. So originally, it was Junie who was scheduled to give the talk today. Unfortunately, he had to reschedule. But I think if June was here, it's likely that one of the things he might talk about are these really amazing optical clocks that his lab is developing. So things that have realized sort of unprecedented levels of frequency stability. So our lab is also interested in optical clocks, but one of the main things that we're focused on is the deployability of these clocks. So we and others in the integrated photonics community are really trying to understand how we can develop components for things like clocks or other types of quantum sensors that can be low size, weight, and power, taking advantage of things like photonic integrated circuits. In our case, we're specifically looking at nonlinearity in photonic integrated circuits. And it's not just about sort of component level performance, but also thinking a lot about the architectures associated with these types of applications, because they tend to be very complicated in labs, and that makes it also very difficult to deploy them. But since I'm local, I thought I would take the opportunity before getting into the main talk to just introduce you to some of our labs and some of the different people that work in the lab, since you can just talk to them directly. So here at UMD in the PSC, we have a lab in the basement, and its main focus is on the development of chip-scale frequency combs and associated technologies. This work has really been spearheaded by Gregory Moy, who's now an associate research scientist here at UMD. He's sitting right over there. And then we work together with Oscar O, who's a graduate student, a bunch of other folks on the College Park campus, so the labs of Avik Dutt, Mohammed Hafezi, and Jan Chembo, and then some collaborations with UMBC, the theory group of Curtis Meniuk, with the Air Force Research Labs in New Mexico, and with other folks at NIST and Santa Barbara and AIM Photonics. Then there's another lab effort that's being done in the sub-basement of the PSC. So this was actually a lab space that's really been graciously offered to us by Alan Migdal and Paul Lett. They've let us kind of set up some experiments inside part of their lab. And so here what we're doing is looking at the interaction of alkali atomic vapors with chip-integrated photonics. The goal is to realize strong light-matter interactions at the level of single atoms and single photons, but now in the context of sort of a room temperature platform. So this work is being done primarily now by grad students Koi Huang and Rahul Shrestha. We collaborate quite a bit with Darren Wesley, who's a process engineer at NIST, who builds all of our devices. And then at UMD, we're working with Alexei and his student Sharoon, and also with Paul. And then from NIST, we have Matt Humman and his student Peter. Okay, and then down the road at NIST, or down the freeway at NIST, we have another lab that's focused on parametric nonlinear processes. Here we're looking at different types of nonlinear optical processes like parametric oscillation and harmonic generation, as well as electro-optic devices. So I'll be talking about work that's been led by Xiuwen Liu and Jordan Stone, who are research scientists at UMD and NIST. Daniel Pimby is a graduate student from UMD. Usman and Zhao Hui are postdocs working now on electro-optics, and Zixuan is a very new postdoc who just started a few weeks ago. And we have some important collaborations here too, especially with Dave Long, who's a NIST scientist who's really helping us understand how to marry together fine-tooth electro-optic combs together with Kerr nonlinear optics. And I'll describe that a little bit later. And then finally, we have another lab at NIST that's now really focused more on quantum light generation and frequency conversion of quantum states of light. A lot of cryogenic systems here that allow us to work with single quantum emitters like quantum dots or color centers and crystals. We also do some of this light generation and frequency conversion using parametric nonlinear optics. A lot of the same folks are involved, but I especially want to acknowledge Marcelo Davanzo and Ashish Chanana, his postdoc. Marcelo has been a long-time collaborator, and he's really leading most of the quantum emitter efforts now. And then finally, we make devices. So these are all based upon photonic integrated circuits. So we build some of these devices in the NIST clean room in Gaithersburg. Here we have access to high resolution lithography and pretty fast sort of throughput. So we can make devices when things are working pretty quickly. But increasingly, we've also been working with some foundries like Ligentech and AIM Photonics to try and realize, sort of transition things that we do in sort of a research facility into sort of a more commercial sort of scale. Okay, so I'm going to start now kind of the proper talk. So what we're basically going to be talking about are sort of deployable optical atomic clocks. I'm going to describe why people are interested in this stuff, talk a little bit about the role of integrated photonics in these types of clocks, and in particular talk about nonlinear components and not just kind of by motivation in terms of how they can be used in these clocks, but also some of the engineering that goes into getting these devices to work. I'll then kind of cover results in two areas. One of them is using this process of optical parametric oscillation in order to create lasers that span a broad range of wavelengths, but primarily focusing on the visible. And then I'll also talk about chip scale frequency combs and their specific use in readout of optical clocks. Okay, so and by way of motivation, the access to really precise and accurate timing information due to GPS and the atomic clocks aboard GPS, this has really revolutionized a bunch of application areas, right? So we obviously think about navigation, but increasingly areas like telecommunications, the distribution of electrical power, emergency services. There's lots and lots of areas that are really benefiting from having access to this, accurate and precise timing information. And then if we go beyond what's possible with the GPS clocks and go to even better clocks, we can think about things like geodesy and even sort of fundamental physics kind of searches. So when we think about the best clocks, they're typically atomic clocks, and we can categorize them based upon whether they involve microwave frequency transitions or optical transitions. And so that's shown in this graph. This is a plot of sort of the stability of the clock as a function of time in decades, basically. And so over the last kind of decade and a half, the optical atomic clocks have really begun to outpace the microwave clocks in terms of their performance, really showing a sizable improvement in stability. Right, and the reason why people care about stability so much is that better levels of stability mean that you have longer time intervals between which you need to resynchronize to GPS. Right, and this is important because it turns out that GPS signals are things that can be relatively easily jammed or spoofed, or sometimes they're just not available. Like if you're underwater or you're in a mine or you're in space, you might not have access to GPS. Go ahead, Trey.
You may want to define stability for some of the graphs.
Sure. So in this case, I'm talking about sort of like a fractional frequency stability. So in a clock, you have an atomic clock, you might have a laser that's stabilized to your atoms, and it's sort of how much that laser is jittering relative to the center frequency is how I'm defining stability here.
I have a question for you.
Sure.
What's the size of these systems, and are any of them, do they involve any refrigeration or something from microwave?
Sure. So I'm actually going to show a plot on that on the next slide. They involve, I think most of them don't involve like explicit cryogenics, but they often involve laser cooling and trapping and things like that. So you are making things cold, but through optical forces. But that's a great segue. So when we think about making these clocks, usable in applications, the stability metric isn't the only metric. So you also have to think about things like the size, weight, and power. So what's shown here is another plot. This is now looking at something slightly different. This is timing error after 1 day. So this is related to stability, essentially. And this is now as a function of size of the clock. But you could equivalently have something associated with weight or power. And then the microwave clocks are the data points in red, and the optical clocks are the data points in blue. And what you generally have is a kind of trade-off where the best performance is achieved for really big systems. Right, so in the microwave domain, the best performance are things like these cesium fountain clocks that take up a whole lab. You also have like these kind of beam clocks that are sort of rack mount instrument clocks, and they sort of give you more moderate performance, maybe something like an error of a nanosecond in a day. And then you have these really ultra deployable chip scale atomic clocks that weigh less than 50 grams and are just a few centimeters in size. And they can be more mass produced, but they give you something like a timing error of a microsecond at a day. But this is still something that's really found commercial applications, in particular with respect to undersea applications where you don't have GPS available. So we sort of see like a similar behavior when we look at optical clocks as well. So the best optical atomic clocks, take up a lab. You can fit it on a trailer if you want to try and move the lab around, but it's still quite big. Over the last couple of years, it's been really exciting that in the commercial space, you have companies like Vector Atomic and Inflection that are making rack mount size optical atomic clocks. So this is based upon transitions in vapors like rubidium or iodine. And then we and a lot of other people were quite interested in trying to understand, what might be possible in terms of making the analog to this chip scale atomic clock, maybe some type of chip scale optical clock, where you can imagine setting a target of something like 100 grams of mass and maybe a length scale on the order of 10 centimeters. So it'll be a bit bigger than what you have with the CSAC, but you might be able to get 2 or 3 orders of magnitude improvement in your timing performance. So maybe hit something like a nanosecond at a day, but be much smaller, or maybe 10 nanoseconds at a day, but be much slower kind of size, weight, and power than these beam clocks or these other sort of rack mount optical clocks. So that's kind of the overall goal. Right, so if we think about what's really inside one of these optical atomic clocks, conceptually it's straightforward. You have a laser, and you stabilize that laser to some environmentally insensitive narrow line width transition in your atomic medium. Right, so once the laser is stabilized, it's really producing this very, very pure sinusoid, and that oscillation frequency is essentially giving you the ticks for your clock. Right, but the optical frequency is very, very high. It might be several hundred terahertz. So there's no electronics that's really going to count that frequency directly. So that's where this thing called the frequency comb comes in. The frequency comb acts as a divider. Just like we might have an electronic divider, this is now a divider that goes between the optical domain to the microwave domain. It's a phase-coherent divider. So whatever that stability is, that fractional frequency stability in the optical domain gets translated down to the microwave domain. And so once it's in the microwave domain, then we have electronics that can count the oscillations, and that gives you sort of the output of your clock. Okay, so where does nonlinear optics come in? Well, it turns out that to hit the wavelengths associated with a lot of these AMO systems, they're often at wavelengths that are not super friendly for direct laser gain. So you might use nonlinear optics as a means to get to that wavelength of interest. And then secondly, this optical frequency comb is generated through nonlinear optics, and it's also stabilized through nonlinear optics. So there's a couple of places where nonlinearity comes into the operation of these clocks. Optical nonlinearity, I should say. So we can think about how these optical atomic clocks might be realized utilizing integrated photonics. And there's quite a lot of effort in the community in working on this across sort of all aspects. So there's groups that are trying to make chip-integrated optical frequency references, so integrating ultra-compact atomic vapor cells with photonic integrated circuits to shine light on the vapor and collect the interrogated signal. There's people that are going beyond working with vapors. I mean, these are kind of maybe the most simple sort of technology to work with, but there's groups that are developing technology for ultra-cold atoms and for trapped ions. And there was actually a JQI seminar last year or the year before that was focused on this type of work. On the laser front, I'm going to go into this in a little bit more detail in a few slides, but there's been quite a lot of work in integrated photonics and trying to make high-performance lasers. And then if we add the nonlinear optics to it, which is going to be my focus, then we might be able to translate those high-performance lasers to wavelengths that we care about for these applications. Various folks are working on things like detection and electronic feedback and control. There are things called kind of photonic interposers. These are basically chips that sort of combine all these different functions together and route signals and spectrally multiplex and demultiplex and interfere signals. And then there are these chip scale frequency combs that are utilized for the division step. So what I'll be talking about is basically the nonlinear optics associated with getting lasers to be at wavelengths that we want, and these chip scale frequency combs for doing division and clock readout. And then it turns out that some of the ways that we're looking at doing this division involves techniques like all-optical synchronization. And that touches upon things like electronic feedback and control, because sometimes you can bypass those things if you can do direct optical synchronization. Okay, so again, talking about these nonlinear processes, I'm really talking about sort of parametric frequency conversion processes. So these are a couple of examples. One is like second harmonic generation. You take light in the infrared, it gets doubled, and you get light in the visible. So this is kind of single frequency in, single frequency out. And then we also have the Kerr comb generation. Here we have a centrally located pump, and we create this rainbow of colors that are, where the pump is centered about that rainbow. So if we think about these parametric nonlinear processes, there's a bunch of kind of basic ingredients for getting this stuff to work. So you want to work with materials that have transparency across your wavelengths of interest. This is kind of obvious, but you want it to be transparent not just to linear absorption, but also nonlinear absorption, because you're going to be dealing with high intensities, because to access the nonlinear response of a medium, you need high intensities. So you tend to want really wide bandgap materials, depending upon where you're going to work. Certainly, if you're working in the visible, you want wide bandgaps. And then you want materials that have large effective nonlinearities. So this is a plot looking at the nonlinear refractive index. This is sort of a metric that judges sort of the strength of a third order optical nonlinearity. And it's looking at it as a function of bandgap. And we're essentially focused on these devices that have, or these materials that have really wide bandgaps for the reasons that I just described in terms of the nonlinear absorption, and looking for things that have pretty high nonlinearities. And so we're often working with silicon nitride, but there's materials like 3 nitrides and so on that might be quite interesting if fabrication could be as compelling in them. We need high optical intensities, right? That's what lets you access the nonlinear response of a medium. The way that we get high optical intensities is using microresonators. So when you confine light to small volumes with high quality factors, so with low losses, then you can generate very large intensities. So even like a milliwatt of continuous wave power going into one of these resonators can give you something like a gigawatt per square centimeter of circulating intensity. And that's how nonlinear optics can be made efficient, utilizing relatively low power continuous wave lasers instead of big pulse lasers that we often use in labs. And then you need to kind of satisfy these basic rules of nonlinear optics. So there's frequency matching or energy conservation. So for parametric processes, energy is completely conserved, meaning that the sum of the input field frequencies needs to equal the sum of the output frequencies of the different fields that are involved. And then we typically also need phase matching or momentum conservation. There's some scenarios where you don't quite exactly need this. But generally speaking, this means that the sum of the input wave vectors equals the sum of the output wave vectors. Right, so when we work with cavities, kind of the effective sort of rule of thumb to get the cavities to be useful in enhancing the nonlinear interaction is that you want to kind of engineer your geometry so that your modes, which are phase matched, are also in frequency alignment. And you also have to take into account how the device is going to behave when it's energized with light. So materials have intensity-dependent refractive indices, and you just have to take into account those intensity-dependent refractive indices when you think about frequency matching the modes. Okay, so the specific platform that we're working with is really well known in integrated photonics. It's stoichiometric silicon nitride sitting on top of silicon dioxide on a silicon substrate. And it basically satisfies in one way or the other some of these different requirements I mentioned. So having a wide transparency window, having a large nonlinear refractive index. A lot of groups have shown high cavity quality factors across a big range of wavelengths. There's lots of ways that we can engineer phase and frequency matching, and I'll talk about that in a little bit. So in terms of cavities, we often think about these kind of 2 general types of cavity geometries. There are these ring resonators. So you can think about that as being like a Fabry-Perot that's wrapped on itself. You inject light into the ring through these access waveguides, and light circulates around the ring many, many times before it leaks out. And so you can support high quality factors across a very broad range of wavelengths. And so these are naturally multi-mode cavities, and this makes a lot of sense for nonlinear optics where you're trying to work with different frequencies. Another type of cavity that a lot of people work on are these photonic crystal cavities. So here you have a Bragg mirror. In this case, it's created by etching this periodic array of air holes. You introduce some kind of defect into this Bragg mirror, and that can localize light very strongly. In these photonic crystal cavities, you often have a very small number of modes. Sometimes it can even be single mode, or you may just have a few modes that are anharmonically spaced. And so it's not necessarily obvious that you would use it for nonlinear optics, but people are kind of trying to develop these things as well. One thing that we've been having fun with over the last few years is just trying to kind of put these 2 things together. So we've been making these ring resonators where we inscribe gratings on the sidewalls. In some cases, these are relatively small gratings, and so they just have like a perturbative effect. They just kind of shift the frequencies of some resonant modes, and that can be valuable. But you can also make them highly non-perturbative, and you can do things like slow down light and localize it and do other fun things. For today, I'm mostly going to be focusing on these basic rings and these grating inscribed rings, which again, due to their multi-mode behavior, is actually quite valuable for the nonlinear optics. Okay, so how do we get like this phase and frequency matching to work? And I should say, the reason why you have to worry about this is that materials have dispersion. So light is propagating at different speed as a function of wavelength. And so in order to get phase and frequency matching to work, it would automatically happen in vacuum. But in real materials, you need something to compensate for this material dispersion. And so one way that we can compensate for it is that we can control the cross-section of the waveguide that makes up this ring. So you can modify like the width of the waveguide. You can modify the thickness of the waveguide. And what that's physically doing is it's impacting the speed with which light is propagating through the ring. And that's shown here. This is a plot of something called the effective index that's related to the phase velocity of light. This is as a function of frequency. And then red, green, and blue are just different cross-sections. And all I'm really trying to say here is that you can actually significantly modify this effective index curve by modifying the cross-section. And so this gives us a knob, basically. This is a way that we can counteract the intrinsic material dispersion by doing this kind of cross-sectional engineering. And in this case, I'm just looking at the same spatial mode, so same transverse spatial mode, and it's just going to be different longitudinal modes, so different numbers of lobes around the azimuth of this ring. But there's nothing that says that you necessarily have to work with just the fundamental mode throughout. So you can think about doing something very similar, but you can work with both the fundamental as well as some higher order modes. Right? So you can imagine a scenario where you manage to phase match a fundamental and a higher order mode, maybe for something like second harmonic generation. That's a common case. And then you can modify the cross-section to make sure that these two phase matched modes are also frequency matched. And so that's kind of a different sort of control knob, and that's because these different transverse modes, they fundamentally have a different effective index behavior just due to the different fraction of the field that's confined in the core versus the cladding, basically.
So you're trying to match the frequency and the index? Or what is the goal? Sorry.
Yeah, so in this case, so you're trying to match in this case, like for a waveguide, you would normally say like, okay, I can send in light at 1550 and at 775, right? So that's frequency matched for second harmonic generation because 775 is twice the frequency of 1550. But then I simultaneously want to have phase matching. So then I want the effective index of propagation at 775 to have, it needs to have like this relationship basically. So in this case, it needs to have the same effective index. And so the way that's done here is that you utilize like a higher order mode. This is like, one example of second harmonic generation, but if you have some other process like third harmonic generation or OPO or whatever it is, this is kind of like a general tool that you might have, that can be apart from this tool, which is kind of doing this cross-sectional engineering, but just working with the same transverse mode kind of everywhere. And this is an example where this is like fundamental and a higher order TE mode, but you could also think about using TE and TM. Most of these things are not perfectly orthogonal in these geometries due to asymmetries and really having the full vector field you have to worry about. And so as a result, you tend to have like interactions between kind of everything if they're kind of engineered to match.
I was wondering, there's some restriction to what mode you can couple to if they're almost orthogonal.
That's right. So in a waveguide, it's a little bit tricky because, yeah, like if we were just coupling into this higher order mode from free space or from a fiber, it doesn't have a very good overlap with like the fundamental mode of a fiber. What we typically do in the rings, because what we're mostly interested in is what's happening in the ring, is the fundamental mode of a waveguide can still evanescently couple into this higher order mode of the ring because, it's not just a direct kind of aligned overlap there. It's an evanescent tail of one interacting with the evanescent tail of the other. It still becomes, can be hard to do that. So you have to play a lot with kind of the geometries and so forth. But, one thing to kind of keep in mind is, yeah, with the rings, kind of all the action is happening inside the ring. The roles of the waveguides are to just convey light into the ring and extract light out of the ring. And so those waveguide parameters can be freely chosen, basically. And typically, we do have to really design those things in order to get light in and out of the ring resonators. Go ahead.
These multiple spatial modes seems kind of not ideal because that would affect your nonlinear feedback. I mean, distributed power now in multiple modes. So ideally, you want a strong curve effect, so you can get, good self-phase modulation if that's distributed in multiple spatial modes.
Sure. So in a ring resonator, these modes are very unlikely to be frequency degenerate. So, we work with these rings where they're relatively small radius and so forth. There's not so many transverse modes. And so for the most part, they're not aligned in frequency. And so, generally speaking, when we work in these systems, we only get kind of the case where we have like this fundamental, sort of phase and frequency match to this higher order mode when we design it to be the case. But the number of sort of like accidental degeneracies that you would have is relatively low. Now in a waveguide, every frequency supports all the different transverse modes. And so in a waveguide, you do really have to worry about, coupling to these higher order modes and so forth. But it's not as much of an issue in the rings because the modes are not frequency overlapped.
So why would you want to do that?
Well, I'm not sure what you mean by distributed. So the field at this, 775 is now in this higher order spatial mode. So indeed, if you look at like the strength of the second harmonic interaction, it's not going to be as strong as having a fundamental mode overlapped with a fundamental mode. That's certainly true. It's going to be weaker when you have a fundamental mode overlapped with a higher order mode. But then the benefit that you have is that you can actually phase and frequency match this process, whereas for second harmonic generation, it's typically almost impossible to use fundamental modes for the fundamental transverse modes at both wavelengths unless you do something like polling. So polling, quasi-phase matching. So this is a mechanism by which you overcome wave vector mismatch by having a grating. That can let you use fundamental modes for both. But so indeed, like if you could use fundamental modes everywhere, it's a more efficient interaction, but just sometimes you can't do it, basically. Okay.
Yeah, I was wondering, like just around this ring, how do you set the node and the anti-node of that mode? Or does it not matter because there's so many wavelengths in the ring that it's going to couple several wavelengths within the coupling region?
Sure. So what I'm mostly describing now are traveling wave modes in these rings. So really, e to the I m phi or something like that in the azimuthal direction. And so you will have something like light that's going into this bottom waveguide, goes and circulates in the ring in this fashion, and then it just exits out.
Okay, so there's no standing wave.
You can have standing waves. So then standing waves happen like when we introduce gratings, you make standing waves. Surface roughness can set standing waves. If I have a quantum emitter that emits in both directions, I can produce standing waves. And then, there can be these different mechanisms that really determine like precisely where the nodes and antinodes are. But for the most part, today I'm mostly going to be focusing on traveling waves. Great, thanks for all these questions. Very good. So then just in terms of kind of more tools for the nonlinear optics, so this is actually one of the grading cases. So one thing we've been looking at with these inscribed gratings is that they kind of provide an additional knob. So what you can do is you can design this grating so the number of periods will really target a very specific mode of the resonator, and the amplitude of the grating will introduce a certain amount of a frequency shift. So what you can do for nonlinear optics is you can have processes that just simply won't work in the baseline ring, and that's actually not so bad because it avoids having kind of competing effects. And then you can introduce this grating that allows a very specific mode to be matched for the nonlinear process of interest. And in this case, you can have interesting things where indeed you can have a standing wave that is then interacting with traveling waves. And so you have some limited sort of efficiency in comparison to all traveling wave interactions and things like that. OK, so I do want to say something about competing processes. So go ahead, Mahmoud.
Is there a reason why the other side of the ring has the atomic crystal and not the exterior?
Yeah, I mean, when we first did this, we thought, oh, in a ring resonator, due to the bending effect, the mode is more likely to get pushed to the outside. And so maybe this would be less perturbative in terms of hurting cues and so on. But we've since also made these on the outer sidewall, and it can work too. So things don't always work no matter what you do, but they often work if you engineer things properly. Okay, so one thing I want to mention is that kind of the different strategies I mentioned with phase and frequency matching, that all sort of assumes that there's only one nonlinear process in the ring. But in reality, there can be other processes, right? And these other processes, they can be competition. So they can deplete your pump power. They can kind of deplete parametric gain. They can introduce noise. And so they can be something that's really unwanted. So for example, I'm showing here a case of a desired process where this pump gets converted into a higher frequency signal and a lower frequency idler. But there's also in principle this process where this same pump generates all these signals and idlers that are just closer to it. And so this is kind of a competing process if the thing I really want to happen is this thing in blue and red. And so when we engineer our devices, we have to worry not just about matching the process of interest, we also have to be sure that other processes are sort of mismatched. And so that's something we have to kind of take into account when we look into how to put devices together. Okay, so hopefully that gives you like a little bit of a sense of like the ingredients that go into this kind of microcavity nonlinear optics. And then I want to tell you a little bit about this application associated with making the nonlinear optics work for translating lasers to interesting wavelengths. So just by way of introduction, of course, in our labs we have a lot of nice lasers. So there's titanium sapphire lasers, depending upon who you buy it from, they're more or less nice. And then you have external cavity tunable diode lasers, and these things can cover a broad range of wavelengths. Actually, over the last few years in integrated photonics, there's really been a lot of development of really nice lasers. This can be based upon the so-called heterogeneous integration of 3-5 gain with very low loss photonic integrated circuits. So heterogeneous integration, in this case, I mean, you really end up having a single chip that has the two things together. There's also so-called hybrid integration, where you have kind of chip-to-chip coupling. And then there's people working on things other than 3-5 gain. So there's been work on chip-scale titanium sapphire lasers as well. And in the best case scenario, people are achieving things like tens of milliwatts of output power, and you can get fundamental line widths that are easily sub 100 hertz, and even hertz level fundamental line widths have been demonstrated now. So what we want to do, though, with the nonlinear optics is like any lasers, the wavelengths that you can access are limited by the transitions associated with your optical gain media. So what nonlinear optics always does is it allows you to access wavelengths that you can't access directly through conventional laser gain, either through processes like second harmonic generation and so forth, or through the parametric gain that you can get from things like optical parametric oscillation. So our idea is that we would like to be able to take all this really nice development that's being done on chip-scale lasers and then combine it with nonlinear optics that's sufficiently efficient that you can work with CW inputs, and then you can cast that light to other sort of interesting colors. Okay, so the specific process which I just mentioned is third-order optical parametric oscillation. So what you have here is you have a centrally located pump, and you create a frequency upshifted signal and a symmetrically frequency downshifted idler. And it's subject to this basic energy conservation requirement. Right? And so this can be really powerful in terms of accessing a lot of different wavelengths, because if you judiciously choose this pump, say you put it at 780 nanometers, then you can create a signal that's at the red edge of the visible spectrum, say at 700 nanometers, and the partner idler will be around 900. Or instead, you could create your signal somewhere in the middle of the visible, say at 600 nanometers, with your partner idler at like 1100 nanometers. Or maybe you can even get deep into the blue, say with your signal at 461 nanometers and your idler at 2100 nanometers. And every set of these, every pair of these frequencies, as well as all the ones in between, can satisfy this basic energy conservation condition. Right? So then what really determines whether you actually generate these colors or not is not just having frequency matching, but also having phase matching. And so the different types of engineering techniques I mentioned earlier to compensate for the intrinsic material dispersion, and doing so while you retain high cavity quality factors, getting light in and out of resonators effectively, and getting rid of processes that might compete with this parametric oscillation process that you actually want to happen. So this is now kind of going a little bit more detail in terms of what an actual engineered device looks like. And so this is a device where we rely upon the engineering of the resonator cross-section to match widely separated signal and idler. And what I'm plotting here, this is a simulation that's looking at something called the frequency mismatch. And so this is the sum of the prospective signal and idler mode frequencies minus twice the pump mode frequency when the pump here is fixed at around 780 nanometers, so around 384 terahertz. And so the condition for a parametric oscillation being matched is going to be when this mismatch is close to 0. So these 0 crossings are going to determine where you generate your signal and idler frequencies. And the Kerr effect, the intensity-dependent refractive index, what it's typically going to do is it's going to shift delta towards smaller values. So that if you look at this curve, the actual shape of this curve and not just the 0 crossings actually matter. So if we zoom in on this region that's close to the pump, this delta is less than 0. And so this is a region called normal dispersion. And what this means is that the modes that are near the pump, they're mismatched. And so it's very unlikely for you to generate light into those modes because they're not frequency matched. And furthermore, when you put more light into the cavity, since delta is going to become increasingly negative, they're going to become even more mismatched. And so this is actually really important. If we don't take care of this, then we pump one of our resonators and it has either anomalous dispersion or zero dispersion, you end up with this. But then at the same time, if all you have is pure normal dispersion, you just end up with CW light. So you don't actually generate any new tones. So what we're really relying upon then to get these zero crossings is a so-called higher order dispersion. So not what's just happening around the pump, but sort of higher orders of dispersion that fold these curves back and make them cross zero. So when things are really properly dispersion engineered, now you can have a single frequency pump, and then you get your one signal and your one idler that are widely separated from it. So this is another example. Here's a case where we're pumping at around 1060 nanometers, and we're generating light at around 780 and 1550 nanometers. And you can see that the generated signal and idler are relatively well predicted from these mismatch curves. And you can look at the threshold behavior, where the threshold for this OPO is on the order of about 1 milliwatt. So it's sort of consistent with these chip scale lasers. Okay, so how do we tune these OPOs? So one thing we can do is we can tune the specific pump mode that we pump. And that's actually going to really, in some cases, really significantly change which signal and idler modes are best matched to the pump. And so that's seen by these different zero crossings when we're just tuning the pump, kind of one mode at a time. And so that's also shown here, where the pump tuning is one of our degrees of freedom, and these different pairs, like the X's or the triangles, those correspond to the different signal and idler mode frequencies. And then we have a second knob, which is geometric tuning. So this is all for a fixed geometry, but we can also vary the geometry. It can be on the same chip, just a different device. And that gives us like an additional tuning knob. And so between pump tuning and geometric tuning, we get coarse steps. And then we can utilize things like temperature to give us fine continuous tuning of our OPO output. Right, so one way that we've tried to realize this in application is to try and generate OPOs that cover the so-called green spectral gap for diode lasers. So I don't have much time to go into why there's a green gap, but essentially if you go to the Thorlabs catalog, you can see that at wavelengths between like 530 nanometers and 630 nanometers, you don't really see any diode lasers. And that's because the constituent semiconductor materials are just not particularly good at generating light in these wavelengths. But OPOs are based upon parametric gain, not direct semiconductor gain. And so they have this opportunity to cover these spectrally inaccessible wavelengths. So what we did is we did the kind of dispersion engineering techniques that I described on the previous few graphs. Here I'm showing one of the devices where we're changing the mode that we're pumping, and you can see this thing glowing different colors. And then this is a series of spectra from a bunch of different OPO devices where you can see, this is just now looking at the visible signal. So there's also a partner idler somewhere out in the infrared. But you can see the ability to cover this full spectral range that constitutes a green gap from about 630 nanometers to 530 nanometers. Although this is coarse discrete tuning, so this is not gap-free. There's not like one device that's covering this entire range, but you can, through a few devices, cover a lot of this range, and then each device has a certain amount of continuous tuning range. Go ahead.
We're looking at, it's like light scattering up some defects in our eyes.
In here, yeah. So this is like, so this is two things. So there's a cartoon that's the illustration showing the waveguide and the ring. But then superimposed on that is a microscope sort of video. As we're tuning our pump frequency, indeed, the generated light in the resonator is scattering. We're not seeing the pump because it's in the IR. We also have an IR filter. And those are the different colors that are generated.
Scattering off some defects.
Yeah, it's scattering off surface roughness, things like that. Yeah.
Well, we're at it. So Michael asked, if you have defects, like isn't left and right running waves, are they degenerate? Why don't they always break into standing waves like somebody else?
Yeah, so what matters is the strength, the coupling rate between clockwise and counterclockwise modes relative to all other loss rates, which includes the intrinsic, sort of radiation loss and scattering loss into anything other than your backwards channel, as well as the coupling to the waveguide. So indeed, when you're in a regime in which you have that backscattering that's stronger than all those things, then you have standing waves, and in the frequency domain, you see a splitting. And sort of the magnitude of that splitting relative to the line width sort of tells you how perfectly you're a standing wave.
You're saying typically for you to smash.
Yeah, so in these resonators, typically we don't have so much backscattering to have standing waves, unless we intentionally introduce those gratings, in which case we definitely have standing waves, right? And you can think about this in different ways. When you have random surface roughness, that random surface roughness in case space is going to impact a lot of different modes because it's not really selective with respect to like one specific wave vector or wave number. But when you have a grading and you've really targeted it, then you can really be more efficient. So it turns out, I guess the upshot is that you don't need gratings with a very large amplitude. As long as they're actually, distributed in k-space where you want them, they can be really effective. Sorry, go ahead. I'll get to it in a second. So in this case, we're tuning at most like 100 gigahertz continuously, and the FSR is about 900 gigahertz. But then we have, I guess, on another slide, we've introduced some heaters. And the heaters are really efficient, so then we can tune something like 1.5 terahertz continuously. So then in principle, if you put all these things together, you can get gap-free tuning across some number of devices, but we haven't done that. What's the what? That'll be on the next slide as well. Sorry, 2 slides. Give me a second. Yeah, so this is just, instead of combining all these spectra into one, this is just showing these spectra kind of one at a time. We can look at things like power. So the power in these OPOs can be on the order of a few milliwatts on chip, up to maybe 10 milliwatts in the red. This is, again, kind of showing the experiment that I showed earlier, where you have infrared 780 light coming in from the right. Here you're generating your different output colors. Maybe I'll skip this because I want to get to the comb stuff a little bit. In terms of line width and so on, so this is a beat note with a free running TISAF, so it's not amazing. This is the frequency noise spectrum, kind of showing that the sort of Lorentzian line widths can be consistent with maybe kilohertz or 10 kilohertz sort of performance. There is additive noise relative to a very quiet pump laser. That's due to the thermorefractive fluctuations in the resonator. You can feed back on the pump to quiet some of the low frequency noise, just as you typically can with lasers. This was actually work that was done here at UMD by Edgar, where we can get output powers as high as about 20 milliwatts on the chip. So this is a conversion efficiency of about 30%. Typically, we have more conversion efficiencies like 15%, something like that. And then this is the thing where when we have an integrated heater, you can really effectively tune these things based upon the refractive index, depending upon temperature. And so then you can continuously tune them by, in this case, as much as like 1.5 terahertz. And so we've done some spectroscopy experiments. I mean, there's been one very basic experiment where we combined sort of this OPO technology with a fine-tooth electro-optic frequency comb. So you can take your OPO, and if it's at the right wavelength, and we have ways to make it at the right wavelength, which I sort of skipped, but you could just do swept wavelength spectroscopy, and in principle, you can see your transitions. And if you did some saturated absorption spectroscopy, you can see things that are Doppler-free and so forth. The nice thing with working with electro-optic frequency combs is that instead of having to sweep anything, you get all your information at once because you have this sort of multi-wavelength laser array. And so we did some experiments first showing that OPOs play well together with these electro-optic combs. And then secondly, kind of putting them into a cesium vapor cell and kind of looking at different hyperfine transitions associated with the D2 states in cesium. So the purpose of this was not to show that we could do any better spectroscopy than you could do with a regular laser. It was just really to show that these OPOs can actually function like regular lasers. And of course, 852 is not the most compelling wavelength because I can buy a laser at 852. But maybe there's some transition in the green associated with iodine or some other sort of thing where this could be more compelling. Okay, so I want to spend maybe the remaining kind of 10, 15 minutes talking about this other topic, which might be of interest to this community, which is on chip scale frequency combs. So again, the role of the frequency comb is to act as a divider in an optical clock. And the specific clock that we've been interested in is this rubidium 2-photon optical clock. So this is a clock where you have a pretty narrow line width transition in a vapor. So you can get 100 kilohertz line width transition in vapor through 2-photon excitation at 778 nanometers. It's quite convenient because 778 can be easily accessed through second harmonic generation of 1556, so you can use telecom lasers. It's not the very best clock performance. It's something like on the order of a few parts in 10 to the 13 has been demonstrated. People think a part in 10 to the 15 is possible. But most importantly for us, you can make these references very compact. So this is work out of the Kitching lab in Boulder where they make this reference something like the size of a deck of cards or a few quarters. And then there is this demonstration lab out of NIST Boulder that we're involved in where you can people have actually shown that you can do the division using microcombs.
Kartik, what's the top? How that?
Oh, this is like the averaging time. Sorry. Yeah, so this is just the scaling of the, yeah. Sorry, that plot is not very legible. So I first want to just remind you about like how a comb works as doing readout for a clock. And so we have like our laser that's stabilized to atoms, right? And then we have our frequency comb. So this is this equally spaced grid of frequency components in the spectral domain. It's a pulse train in the time domain. And each comb tooth can have its frequency written in this very simple fashion that depends upon the spacing between the teeth. That's called the repetition rate, some integer multiplier, and the offset with respect to DC called the offset frequency or Kerr envelope offset frequency. So the first step is that you lock one of the teeth of the comb to your clock laser, which in turn has been stabilized by atoms. Right? So this is typically some kind of like phase lock loop. And now you've pinned one of the degrees of freedom of the comb. The next thing you do is you lock the Kerr envelope offset frequency of the comb. This is typically done through a process called self-referencing. So you take a low frequency comb tooth, you double it, and you compare it to a high frequency comb tooth. And if you just do a little bit of algebra, you'll see that that retrieves the Kerr envelope offset frequency, which you can then stabilize by feeding back to the pump that generates the comb. This does require a comb that spans an octave in bandwidth, so that's sort of the trade-off. But now when you've pinned one comb tooth to the clock laser, and you've pinned the Kerr envelope offset frequency, now you've pinned 2 of the degrees of freedom of the comb. So that means that your clock laser frequency just gets divided onto the repetition rate of your comb with the division factor that's given by the integer associated with the comb tooth that's locked to the clock laser. And so this thing is called optical frequency division. And you have division not just of the frequency, but also of its noise. And then, if you do a little bit of algebra, you can see that the fractional frequency stability remains the same. So the noise on the clock laser divided by the clock laser frequency equals the noise on the repetition rate divided by the repetition rate. If this really works as a phase-coherent divider, that the comb is not introducing any noise, or it's not typically trying to improve the noise of the system. It's just translating it from one domain to the other with this division factor. Okay, the other thing I should mention is that for our types of resonators, they can often have a pretty big spacing between the comb teeth, and so we might require another stage of division. Okay, so very briefly, if we compare our OPOs, these create a single signal and single idler. The combs, instead, when you pump them, you create this rainbow of frequencies, right? And so the spectra look like, this versus that. And when we look at these combs kind of more carefully in terms of like what's happening conceptually, there's a nice illustration that Sean from NIST made. Oops. And so what we're really dealing with, for the most part, in our work, is this regime called dissipative Kerr-soliton formation. So solitons exist due to this double balance of dispersion and nonlinearity and parametric gain and loss. So what's happening is you inject CW light into the system. There's some initial sort of pattern formation associated with modulational instability, and eventually you can produce these solitons, which circulate around undisturbed in this ring, and they get periodically extracted by this access waveguide. So that periodic extraction gives you a pulse train in time. If you have the pulse train in time, that gives you the comb in the frequency domain. So in terms of things I've mentioned earlier, like dispersion engineering, there's this key difference that in the OPO, we use normal dispersion near the pump, specifically to suppress processes that are going to generate light near the pump. For the Kerr comb, we use what's called anomalous dispersion near the pump because we want to promote those processes. So the anomalous dispersion means that when you energize a resonator with light, the nonlinear shifts associated with the nonlinear refractive index actually bring those modes into closer into spectral alignment. Okay, so this is what what kind of our engineered microcombs looks like. This is pumped at around 1 micron. On the high frequency side, it produces light up to around 390 terahertz or so, about 770 nanometers. And then on the low frequency side, it produces light down to about 192 terahertz, or around 1560 nanometers. And so this spans an octave, which is associated with that self-referencing I mentioned. We used to make these things exclusively at NIST. We can now work with some foundries that have higher throughput lithography capabilities, so you can pack a lot of these comb generators on one die, dozens of die on a reticle, and dozens of reticles on a wafer, so you can really try and scale up what you can look at with these sorts of systems, at least within a certain window of parameter space. It doesn't always work well with the foundries, but when it does work well, we can generate these octave-spanning combs pretty reliably. Okay, so I mentioned like a few years ago in Boulder, there was this demonstration experiment where they utilized these microcombs as a divider for this 2-photon clock. And sort of the key technical result was that this stability was something like 15 times better than what you would get out of a chip-scale microwave atomic clock. And so that's about the performance. But then the downside of this work, which was really quite nice, was that is quite complicated. So this is sort of showing the overall system diagram. Some things are still complicated in our work, I can't lie. So we have to use 2 stages of optical frequency division because our combs are so small that the spacing is really high. But there are other things that we have tried to improve upon. So these combs were actually centered around the telecom band, so they needed second harmonic just to access the rubidium wavelengths. We can now access those rubidium wavelengths directly. There was also not enough power for self-referencing directly, so they had to use other lasers and then lock these other lasers to the comb and keep track of beat notes. And that's ultimately why there are 5 phase lock loops associated with making this clockwork link to the laser.
Kartik, you said that you have a frequency divided twice. Is that because you need to digitize the microwave machine, or what do you do?
It's a good question. Yeah, so I was a little bit unclear here. So the comb that we're working with, the spacing between the comb teeth is like 1 terahertz. So we can divide 385 terahertz to 1 terahertz, but then we don't have any electronics that's going to detect 1 terahertz. So we need that second stage of division to divide from like 1 terahertz to say 20 gigahertz, and then that's something we can count.
Schematic there to the right.
Yeah, so this one is a 1 terahertz resonator, and this is a 22 gigahertz resonator. And so this specific scheme involved 2 different soliton combs and figuring out how to make them interlock in such a way that you can maintain this phase coherent division. So both of these things are acting as actual dividers. And then I'll briefly be talking about other approaches for doing this that can involve like electro-optics or other techniques. But okay, so one thing that we've been looking at, and maybe this is the last sort of main technical concept I'm going to be bringing up, is all optical synchronization. So what we've been quite interested in is, if we take this clock laser, which we need for our clock, and we inject it into the same resonator that generates our frequency comb, is there a regime in which this comb can really lock on to the clock laser? So by that, I mean one of the comb teeth can actually get into precise spectral alignment with this clock laser, both phase and frequency lock. So it's really a phase lock, so that this clock laser essentially becomes part of the comb. Right, and I'm going to talk a little bit about why and when that happens, but first I want to say like what it means if that does happen. And what it really does is, first of all, it gets rid of one phase lock loop. We always have to lock the comb to the clock laser, but now we can do this through optical synchronization instead of electronic servo control. And in the lab, servo feedback control and so forth, you do it all the time, but these things actually take up a decent amount of power, and they're kind of big. So for deployability, it's nice if you can get rid of them. The second thing is that if this synchronization happens in the right region of frequency space, then we can actually think about doing things like doubling this clock laser, which is now part of our comb, and using that in self-referencing. And the clock laser will have way more power than one of our comb teeth would normally have, and so that really helps us with the self-referencing task. Gets rid of auxiliary lasers and maybe a couple of additional phase lock loops. Then more generally, I mean, it's just interesting to think about ways that you can utilize all optical synchronization. In this case, it's between a soliton comb and a reference laser, but it can be between different soliton combs and so forth. And these sorts of things can provide simplification, but of course, they might also have their own challenges and things that need to be tested, sort of at a metrological level. I do want to mention that this has some similarities to this phenomenon of optical injection locking, right? So it's often used in labs that you have a high power Fabry-Perot laser. You like the power, you don't like its spectral characteristics. You inject a narrow line with seed into that, and you basically make that high power laser follow the narrow line with injected seed. And so what we're really trying to do here is, in some sense, injection lock the comb to this clock laser. All right, so if we think a little bit about the specific context of this rubidium 2-photon clock, what's kind of interesting for us is that I already mentioned that because the clock transition is at 778, you often start with a telecom laser and double it in order to reach 778. And so we can actually use what's already done in these 2-photon standards, like from the Air Force. And just by tapping it off, we can really improve our way to self-reference our comb, because we can tap off some of the 1556 and use that to synchronize the comb to the clock laser. We can tap off some of this doubled light, and because the clock laser is now part of the comb, we can use that tapped off doubled light for the self-referencing. And so this really provides some really significant level of potential simplification. And this is showing, actually in the lab what happens when you have, one of these combs that spans a full octave, and you can really see that you can have the spectral tones in alignment with F and 2F, for example. Okay, so a little bit more about the physics, right? So what we're basically relying upon in this synchronization is the cross-phase modulation. That's due to the Kerr nonlinearity that's already inside this ring. we needed to lock both the group velocity and phase velocity of the soliton and this intercavity reference laser. Right, and so this kind of dual group and phase velocity locking, it doesn't always happen. So we have plenty of situations where you don't see anything. If you work in a low dispersion regime, then you often will see just group velocity locking. So you can create additional sort of comb teeth that have the same comb tooth spacing because that's associated with the group velocity, the round trip in the resonator, but it has a different phase velocity. And so this second comb that you create is actually offset with respect to the first one. But under the right conditions where your comb tooth is sufficiently close to your injected laser, you can achieve the phase locking as well. And so then the comb tooth snaps onto the reference laser. And in that case, we have synchronization, and this can be well modeled both through kind of more detailed nonlinear dynamics modeling, as well as kind of more universal synchronization models. Okay, so I think I'm running out of time, so I will just kind of wrap this up. So just in terms of seeing synchronization in the lab, the types of things we look for are when we're outside of synchronization, there's a finite beat note between this injected laser and our comb tooth. When we're actually synchronized, that beat note goes away because things have locked on. We can look at how the synchronization window scales with things like the power of the clock laser and the comb tooth, and we can see a scaling that sort of matches what we expect from modeling. We can look at the repetition rate control. So when you have the synchronization, the comb is basically doubly pinned now. There's the original pump that generates the comb, and now there's a second laser that you've synchronized it to. So if you do things like wiggle the frequency of that second laser, it's going to impact the repetition rate of your comb. And we see that. We see the repetition rate of the comb change as we wiggle this reference laser. And the slope of this change is just associated with the number of comb teeth between the two lasers. And so again, this is optical frequency division, essentially. So, did you have a question?
Like, I was going to ask, I think maybe this is the answer. Like, the original pump frequency is fixed because you send it in,
right?
And then the reference is fixed, and so it's the repetition rate that adjusts to match.
That's right. The repetition rate adjusts to match where these things are.
Oh.
Yeah. I should say, yeah. So in this case, obviously, we showed like, oh, we wiggle it, so we didn't quite make it fixed, but we wiggle it in order to see this kind of division. But of course, instead of explicitly wiggling it, you can just look at noise. So we can look at like the reference laser noise, which is shown in blue, and we can look at our repetition rate noise, which is shown in green. And we see that they match pretty well when you take the reference laser noise and you divide it by the optical frequency division factor. So indeed, the repetition rate is adjusting itself to match what these lasers are doing. And that's actually, it's very deep. And unfortunately, I don't have enough time to talk about it. This is just showing that you can actually make this repetition rate beat note very narrow, just a few hertz. Well, I'll just say that, one of the things it really does is it really means that this comb is now, a lot of its properties are really controlled by these two lasers. So a lot of the things associated with like noise propagation in this comb and the impact of things like thermorefractive fluctuations, they begin to get bypassed because you have this synchronization. And it's similar like when you do active servo control. Of course, you're always trying to reduce noise when you do active servo control. It's just now you can do this all optically, sort of automatically with the synchronization and really show that you see these effects. So maybe the final thing, because I know I'm running out of time, is to just say that we have been able to self-reference these combs. In many cases, the big challenge is so we can take the reference laser that synchronizes the comb and we can double it, compare it to a high-frequency comb tooth. But we can actually have a pretty large Kerr envelope offset frequency because the spacing between the comb teeth is large, so the Kerr envelope offset frequency can be large as well. So we have to use things like auxiliary electro-optics to really be able to detect that CEO frequency, but then we can feed back on the main pump and stabilize. And then similarly, we can measure our repetition rate, which is very large, 1 terahertz, again, by using auxiliary electro-optics. That's right. So basically what we're doing is we're taking these two comb teeth that are separated by a terahertz, and then we're sending them into phase modulators. And then the phase modulators basically create a bunch of sidebands, and eventually you're going to have the sidebands that sort of meet in the middle, and that gives you a beat frequency. And so when you're just doing repetition rate detection, you can just know your driven RF frequency and that beat frequency. That'll give you like a measurement of your repetition rate. But then when you want to really do division, then you need to feed back on what you're sending to the phase modulator, and then you can really get division. So that's like an electro-optic frequency divider instead of, a different type of frequency divider, essentially. I'm calling it auxiliary because, this stuff is all kind of chip integrated, and this is basically a rack of EO space phase modulators and microwave amplifiers. EO division doesn't necessarily increase your noise floor if you really do true division. When we don't do division, when we were just doing modulation, then indeed we're going to be limited by the synthesizer noise. But if you actually feed back on that synthesizer when you do this, then you can actually do proper division. Okay, so I mentioned something about the noise properties of these combs. Unfortunately, I don't have time to go through it. It's just to say that you really can impact the noise performance by doing the synchronization. So this is kind of where we are. So we've been able to make this divider that can go from 385 terahertz to 1 terahertz. If we want to go to lower frequency that you can actually detect, we use these electro-optics. We would like to get away from using this sort of rack mount sort of stuff that's really high power. So we're looking at utilizing chip scale electro-optics, which people have shown can be much lower in power. There's other techniques that have been pioneered by the Weiner group that allow you to do division from like a terahertz down to some much lower frequency. We're looking at maybe trying to do second harmonic generation on the chip, which is something we've looked at in the past. And then we'd also like to make the lasers that drive our combs, more chip integrated technologies. And then the final thing I'll say, and I'm not going to go into any of these things in detail, but I focus a lot on like this application, this clock application and so forth. But the physics of the synchronization in these systems is really quite fun. So Greg in particular has really looked at a lot of different things. He's looked at things like the resonators can support multiple soliton pulses, and normally they have a jitter. But when you do synchronization, you can get rid of their relative jitter. And so there's ways that you can make multi-soliton states as quiet as single soliton states. He's recently looked at chaos in this system, where if you phase modulate your reference, you create a pair of attractors, and you can have hopping of your repetition rate between these two attractors. This is mostly fun, but maybe there's something we can do with the chaotic stuff. There's also different ways you can engineer synchronization. So with that, I want to again thank all the people who make the work happen. There are a few folks here who recently finished in the group. Yi-Sun is back in China. He was working on OPOs. Michael is back at the Sensor Science Division at NIST. She was working both on Kerr combs and OPOs. Roy was working on the rubidium photonics. He was back in Israel. And then Edgar is now working at IonQ. And then I should thank NIST, especially the NIST on a Chip program, the Air Force, and DARPA. And I can take questions.
Yeah, after this question would make sense. When you say after synchronization, like the relative noise just vanish, or like when you say the when you lock to the cone, like the noise of the lock like cone is the same as the injection. Like I guess the question is there a fundamental limit of that process? Like and if you imagine like the noise of the injection is like gonna become smaller and smaller at some point, like do you see the effect of this? Like,
Right. So these are both very good questions, and probably it would be good to maybe talk in a little bit more detail. I'll mention a couple of things. It's not going to get completely to what you're fundamentally asking, but one is like, so what do I mean by noise? So one metric of this is looking at like the comb tooth line widths. And so typically when you just have one pump, you see the line width increase as you go away from the pump. And that's like the transduction of like the noise on the pump laser onto these other comb teeth. And so then when you do the synchronization, this really flattens out. It actually follows the same type of noise propagation model. It's just now instead of being pinned at one location, it's pinned at a pair of locations. So it's not like noise completely goes away. It's just reduced it. And then if you can also look at things like repetition rate noise, and our colleagues in Baltimore, we've looked at some of these things theoretically as well. And so there's noise damping that happens. The sort of the strength of the dampening, or the strength of the damping depends upon kind of where you are in the synchronization window. And the rate of damping depends upon things like the photon lifetime. And so you're only going to damp, at frequencies that are below that. Eventually, if you're faster than the photon lifetime, then you're not going to be damping anymore.
lifetime means in this case the lifetime induced by the decay rate induced by the lens.
Yeah, this would be like if you have the cavity mode, basically like what its line width is. There's also interesting questions about what the lifetime of the soliton is and so forth, but I don't know if I can answer those well.
Let me have one more question due to time.
So I usually work in, electronics and superconducting circuits. You mentioned, the fractional frequency change, and then you later showed a line width, but how are those two related? Do you just have a really good line width, but then fractional frequency change depends on your feedback loop in some way?
Yeah, so I think so. So in general, like so sorry, are you talking about? I missed the.
All these teeth, you have these cavities,
Right.
resonances,
Right.
traveling waves. So that has some sort of line width to it relative to the frequency.
Sure. So the cavity mode line width does ultimately impact, what your frequency noise performance is going to be on these generated tones. But the generated tones are much narrower than the cavity modes, right? So and these nonlinear processes, right, like the frequency matching and so forth, the energy conservation associated with the parametric nonlinear process, like that's really exact. So when you're above threshold, you're not going to just generate light that fills the entire line width of the cavity. You're going to be much narrower than that. But you still have some frequency jitter, right? And so if I look at like my spectrum of frequency noise, I'm going to have some frequency jitter. And that can depend upon things like the thermorefractive fluctuations of the cavity, or it can depend upon, the pump laser fluctuations, or both typically.
All right, so it's not great line within the cavity, but you get your nonlinear processes there, so you need that cavity for the nonlinear process.
Right. So the cavity mode itself, its line width, which is a representation of its photon lifetime, like we may not have the highest Q cavities. So when we have a Q of 1 million or a few million, our line widths are 100 megahertz or a couple hundred megahertz. The generated tones can be much narrower than that. But indeed, the role of that high Q is to help promote the nonlinear process. That's also promoted by having strong field confinement and so forth, and a large material nonlinearity and things like that. But then, yeah, like if you look at something like people have looked a lot at this in the context of like lasers, so you can just make a laser cavity, and having a really, sort of high Q cavity can ultimately help you get a better, fundamental line width associated with your laser oscillator. But then that might come at some cost of having a bigger cavity, which might require you to have, other things depending upon what you're doing.
All right, well, let's thank Kartik again.